In this video, we are going to look at inverse functions, the conditions for their existence, and obtaining the definition of an inverse function. So, what are inverse functions? In the previous video, we have learned what are functions. You put a lemon into the juicer, you get lemonade. You can think of an inverse function as a time machine which undoes the process. So, imagine you have a cup of lemonade, you put it in this time machine, and it goes back in time to give us the lemon back. So the inverse function is like an undo button, helping us undo whatever the original function has done. This also means that the original output of the function is now the input of the inverse function, and the original input of the function now becomes the output of the inverse function. Like the definition of a function, there are also conditions to be satisfied in order for the inverse of a function to exist. Let's say now my function is an iron recycling plant. It takes in ions of all forms and melts them into molten iron. If we were to look at the reverse process and we put molten iron into the machine which undoes the melting process, the machine will have trouble identifying which shape to transform the molten iron into. This tells us that 2 to 1 functions, or more generally, multiple to 1 functions, do not have an inverse, because the inverse function will not know what to undo. Therefore, the condition for an inverse function to exist is that the function must be a 1-1 function. We can make use of the horizontal line test to determine if a function is 1-1, and hence whether its inverse exists. Take for example the two graphs on the right. We will first draw a horizontal line of y equals to k across each graph. If the horizontal line cuts the graphs at a maximum of 1 point regardless of its position, then the function is 1-1 and its inverse exists. However, if the horizontal line cuts the curve at 2 or more points, then the function is not 1-1 and its inverse does not exist. Let's now take a look at some simple examples to illustrate this. In example 1a, we have the function fx equals to e to the power of x squared for all real values of x. The graph of this function looks like this. And if we draw a horizontal line across, we see that the horizontal line cuts the curve at more than 1 point. And therefore, the function f is not 1-1 and its inverse does not exist. This sentence here is a standard sentence that you should memorize and apply for all questions that ask you to prove that the inverse does not exist. In example 1b, we have the same definition but a different domain, now restricted to positive real values of x. And thus the graph looks like this now. And if you were going to draw a horizontal line across, we can see that this horizontal line cuts the graph at most 1 point for all the values of k that we draw. And we can conclude that this function of f now, because of its new domain, it becomes a 1-1 function and therefore its inverse exists. So we should conclude the proof by adding this following statement. This example also illustrates that although definition of the function can be the same, the domain will actually play a role in determining whether the inverse exists or not. As shown in earlier examples, the domain plays an important role in determining whether the inverse exists. In this example, we are asked to change the domain such that we can make the inverse function exist. First, let's prove that the inverse function does not exist for the original domain. So we can draw the graph out for the original domain. It will look like this. And this point is 3, this point is at 1, and this is 2. And it goes all the way to infinity. And if you are going to draw a horizontal line of y equals to k, we can clearly see that the horizontal line cuts the graph at 2 points for some values, and therefore we know that this is not a 1-1 function, and therefore the inverse does not exist. Now, if we were to amend the domain of this function, how can we make sure that it cuts at only 1 point at most? So the trick to do that would be to start from the minimum point and go towards the end. And we see that once we start from the minimum point upwards, it will no longer cut the graph at 2 points, and therefore whatever horizontal line that we are going to draw, it is going to cut the green color curve at just one point at most. And therefore now, when we change the domain into the domain of the green color curve, we know that it is going to be a 1, 1 function, and therefore the inverse is going to exist. And in this case, we can say that the new domain of f is going to be from 1 to infinity, including 1, excluding infinity, which means the minimum value of a will be 1. Other than proving whether the inverse of a function exists, we are also interested in finding out the actual definition of the inverse function. To find the definition of the inverse function, we have to simply follow the following steps using this example over here. First, we let y equals to fx, meaning we can say that y is equals to e to the power of 2x plus 1. Next, what we want to do is to rearrange the equation to make x the subject. So we have ln y equals to 2x plus 1, and therefore we can say that x is equals to ln y minus 1 over 2. What this does is to write x as f inverse y, and we can say that f inverse y is equal to gy. So what happens is, for y equals fx, it becomes f inverse y equals to x. And we see that f inverse y is equals to x, and also x is equals to gy, which means that these two terms must be equal. And therefore, I can say that f inverse of y, it must be equals to ln y minus 1 over 2. And if I change all the y's into x, I will get f inverse x equals to ln x minus 1 over 2. Next, we have to also determine the domain of f inverse, because remember from earlier, we have established that as long as we are defining any function, we need to give the domain. And to get the domain of f inverse, it is basically the range of f. So we have to now find out what's the range of f. Okay, domain of f inverse equals to the range of f. And in this case, it will be from 3 all the way to infinity. And therefore, now we have the definition as well as the domain. We can finally write down the proper inverse function in the required form, which is f inverse colon x. It is being mapped into ln x minus 1 over 2 for x more than 3. And this is the definition of the inverse function. Example 2 requires us to find the inverse of a quadratic function. For quadratic functions, in order for us to find the inverse, we will have to first perform completing the square in order for us to be able to rearrange the equation. Let's find out how we can do so. So first, let y equals to fx. So we have y equals to x squared minus 4x plus 6. And we can complete the square to get x minus 2 squared plus 2. It is only after completing the square then we are able to very easily manipulate the equation to make x the subject. So from this equation, we can say that y minus 2 is equals to x minus 2 square, which means that x minus 2 is equals to plus minus of square root of y minus 2, and therefore x is either equals to 2 plus square root of y minus 2, or x is equals to 2 minus square root of y minus 2. Now, there are two expressions for us to choose. We have to choose the appropriate one. And how we can choose is by looking at the original domain of the function. We know that x must be more than or equals to 2. And we also know that square root of any number is always a positive number. Therefore, we want to pick this expression with the positive square root, and we do not want this negative square root as the final expression. Therefore, we are going to reject this expression. So based on this, I can say that f inverse of y is going to be equals to 2 plus square root of y minus 2. And with that, let's proceed on to change all the y into x. I will have f inverse x equals to 2 plus square root of x minus 2. And now we have to find out the domain. The domain in this case will be the range of f, which is the same as the domain x must be more than or equals to 2. Therefore, I can finalize the entire question by saying that f inverse x is going to be mapped into 2 plus square root of x minus 2 for x more than or equals to 2. For any function that has an inverse, if we sketch the graph of y equals to fx and y equals to f inverse x, we will notice that they are actually reflections of each other about the line y equals to x. In other words, given the graph of y equals to fx, if we wish to draw the graph of y equals to f inverse x, we simply have to first draw y equals to x, then reflect y equals to fx about y equals to x to obtain the graph of y equals to f inverse x. Also, this observation has an implication. That is, if we are asked to solve for the equation of fx equals to f inverse x, we do not have to solve this equation directly. Instead, we can simplify the problem by solving for fx equals to x instead, since all three graphs intersect at the same point. Let's apply this concept in example 3. Now, we have the function of fx equals to x squared minus 4x plus 6 for x more than or equals to 2. And we are asked to solve for the equation of fx equals to f inverse x. Therefore, we can say that the solution of fx equals to f inverse x is the same as the solution of fx equals to x, which means we just need to solve for the equation of x squared minus 4x plus 6 equals to x, which is the same as x squared minus 5x plus 6 equals to 0, and we can factorize it into x minus 2, x minus 3 equals to 0, and x equals to 2 or 3. And since the domain is such that x is more than or equals to 2, both solutions are accepted, and these are the two solutions for the solution of the equation of x equals to f inverse x.